All right, in this lesson, we're going to keep working with trigonometry, trig ratios between 0 and 360 degrees. In other words, we're going to be considering trig ratios on the Cartesian plane. We've seen in previous lessons that we can put angles on the Cartesian plane. We can consider an angle we can always measure angles at the origin. We can consider the x-axis, the positive x-axis, as our starting point always, which we call our initial arm. And then if we go clockwise, then we can go until a certain point, such as here, call that the terminal arm, or we could keep going to here or here or here. We could go all the way around to 360 if we wanted to. So our trig ratios, as we know, only go for our right angles between 0 and 90 degrees. But if we extend the concepts, we can do trig ratios between 0 and 360 and beyond as well. So let's consider for a moment a point on the Cartesian plane. Call it xy, so it could be any point. I mean, this point looks like maybe could be the point 4, 3, but this, that's just where this point looks like it is, but it could be anything. So a point on the Cartesian plane. If we were to take that point, imagine that this point is on some sort of string attached to the origin, maybe by a pin, and we were to go all the way around like this, around in a circle, then obviously that string would form a full circle around the origin. So I'm just suggesting that that point is connected to the circle. And in fact, the connection between this point xy and the circle is that the distance of this point xy from the origin is going to be the radius, right? If I connect the origin to the point, then I get the radius of the circle. Also, since this is the origin, which is the point 0, 0, if I wanted to get from the origin to this point without going along the radius, if I wanted to only go horizontally and vertically, I would have to go this far to the right. Well, how far is that? Well, that's x units to the right. And I would have to go up this far. How far up is that? Well, that's y units. And then if we just transpose this over to here, it's the same distance. So it turns out that this point xy forms a triangle, which you can see right here. And that triangle, we can know what all three side lengths of this triangle are if we know what the point xy is. This side down here is going to be the length of that side is going to be whatever the x-coordinate is. This side right here, the length of it is going to be whatever the y-coordinate is. And the radius can be easily found just by using the Pythagorean theorem. Remember, the Pythagorean theorem is x squared plus y, well, it's not x, it's a squared plus b squared equals c squared. But in terms of this, x and y are our a and b, and the hypotenuse is our radius. So the radius is going to equal the square root of x squared plus y squared, which is pointed out over here, although it's explained in a slightly different way. In this one, it's talking about it as a circle, the equation of a circle, which we also know is x squared plus y squared equals r squared, and we could rearrange that to get r equals the square root of x squared plus y squared. Exact same results. The only thing is I'm using Pythagorean theorem to explain it over here, and it's using the equation of the circle over here. But either way, we get to the same point, that we can know what the radius is if all we know is a point. So we can know x, y, and r, all three sides of this right triangle, simply by knowing what a point is. And that's good because the opposite side, the radius is, opposite. Brain hasn't woken up yet today. The radius is our hypotenuse. The opposite side, as I'm sure you know, is over here. That's y. Opposite from our angle, which is always at the origin. And x is the adjacent side. So I've got three side lengths to choose from to make trig ratios up, and all I needed to know was a point on the xy Cartesian plane. So Since sine is equal to opposite over hypotenuse, but opposite is the y value and hypotenuse is the r value, then I could rewrite sine in terms of those three, x, y, and r, and I could rewrite it as y over r. Sorry, my iPad's acting a bit funny. I'm not sure why it made my y go wonky. And it happened again. Dear, oh dear. Hopefully that won't keep up. Let's try one more time. Y, there we go, over r. All right. So y over r is the same as opposite over hypotenuse, so that's my sine ratio. Cosine is adjacent over hypotenuse. Well, adjacent is just the side x, and the radius r is my hypotenuse. So cosine, it turns out, is x over r. And tan is opposite over adjacent, so that would be y over x. So let's put this together. A point on the terminal arm of an angle, theta, is -3, -5. Determine the primary trig ratios. Let's draw ourselves a picture. Do it over here. So -3 is on the x-axis, -5 is on the y-axis. That would be down here somewhere, right? If -3 was about there, -5 on the y-axis down there. I could draw a circle, although I'm not a great circle drawer as far in there. If you can see what I mean, I'm not the world's best circle drawer, but, I'm trying to do something like this. But I don't need the circle, really. All I need to know is that we always start on the positive x-axis for our initial arm. We go around until we get to a terminal arm. And in this case, the terminal arm is going straight through this point, which I already pointed out was -3, -5. So this angle we call theta, and it's an angle that's greater than 90 degrees, of course. Based on what we know, being in quadrant 3, it's got to be somewhere between 180 and 270 degrees. But I can get the trig ratios, and I can figure some stuff out based on this. So I can maybe just draw a right triangle from this point to the x-axis. I pointed out before that we always create our triangles to the x-axis and never to the y-axis. And I can know some side lengths. Again, the x-coordinate gives me this side length here, because that's my distance from the origin over. The y-coordinate gives me this side length here, because this -5 is from the x-axis down to the point, so that would be 5 units. So I've already got 5 and -3, the opposite and the adjacent side. And I can find out what r is simply by calculating using the Pythagorean theorem again. So r is equal to the square root of -3 squared plus -5 squared, which is 9. A negative number squared is always positive, so it's 9 plus 25. So the square root of 34, that could be changed to a decimal. It's not going to be a perfectly round number because square root of 36 is 6. Square root of 34 is not a perfect square. So maybe I'll just leave that as a radical for now. So just write it as square root of 34. So now I've got, and I'll highlight it just so it pops out a little bit there. Now I've got r and x and y values. So if I want to find the primary trig ratios, I know that sine theta is going to equal opposite over hypotenuse. And opposite, again, is always the y value. Actually, let me go back and put it this way. Sine is equal to y over r, we just said above. So that would be -5 over the square root of 34. Cos theta is x over r. So that would be -3 over the square root of 34. And tan theta is equal to y over x, which would be -5 over -3 I would definitely cancel out those negatives. I'd tidy it up. In other words, 2 negatives make a positive. I'd just write it as positive 5/3. Just a word of warning, I would consider this to be an incomplete answer. If you gave me that kind of answer on a quiz or a test, I would say you should be tidying it up more. We never want to leave negative over negative like that. So that is incorrect, at least not finished. This is the correct answer. There's all 3 trig ratios. I talked a bit about the cast rule in a previous lesson. It turns out that each of the 3 trig ratios will be positive in 2 of the 4 quadrants, and they're going to be obviously negative in the other 2. So consider that sine theta equals y over r, and recall that r is always positive. When y is positive, therefore, sine is going to be positive. Which quadrants is y positive in? Well, if we look at this chart here, the y-axis is this vertical axis. Y values are positive when we're dealing with numbers above the x-axis. So for which 2 quadrants are abutting on this highlighted value? Well, quadrant 1 and quadrant 2 are both have positive y values. And as I already pointed out, r is always positive, so sine would be positive in quadrant 1 and quadrant 2 because you're going to have a positive y value over a positive r value, and so those would be both those quadrants have sine as positive. So maybe I'll just list the things that are positive in each quadrant. So sine is positive here and in quadrant 1. So quadrant 1 and 2. Now, cosine is identified as x over r. When x is positive, cosine is going to be positive. Which quadrants is x positive in? Well, this is the x-axis here, and we know that to the right of the y-axis is where we have our positive x values. So in other words, here, that's positive x values. So the 2 quadrants that butt up against that would be quadrant 1 again and quadrant 4. And so I guess I should write that in here. 1 and 4. And now tan theta is equal to y over x. When y over x is positive, tan theta is going to be positive. But y over x is going to be positive not just when x and y are positive, but also when x and y are both negative, as long as they have the same signs. So in other words, here in quadrant 1, if I was to do y over x, my y value is positive and my x value is positive in quadrant 1, isn't it? So tan is going to be positive in quadrant 1. But in quadrant 3, x is negative and y is negative. So I'm going to have a negative over a negative, which I just pointed out above simplifies. Just up here, we saw that negative over negative becomes positive. So in quadrant 3, tan is going to be a positive value. So tangent is also positive here. So tan is positive in quadrants 1 and 3. So it turns out that all of them are positive in quadrant 1. Just sine is positive in quadrant 2. Just tangent is positive in quadrant 3. And just cosine is positive in quadrant 4. So if we take the first letters from all, sine, tangent, and cosine, then we can make the acronym CAST. Now, we have to start down in the 4th quadrant to make this work. Otherwise, I'd have ASTC, which isn't a word. So if I start at quadrant 4 and go this way, then I can spell the word CAST. And so it's just a way to remind us of what's positive in what quadrant. All trig ratios will always be positive in quadrant 1. Just sine will always be positive in quadrant 2. So what does that mean about cosine and tangent? It means that cosine and tangent will always be negative in quadrant 2. Tan is the only trig ratio that will be positive in quadrant 3. That means that sine and cosine will be negative in quadrant 3. And cosine is the only ratio that's positive in quadrant 4. sine and tan are negative in quadrant 4. So that's what the Castor rule is all about. A point, negative 5, 7, is on the terminal arm of an angle in standard position. So in standard position, we got this point, negative 5, positive 7. So that's up here. And terminal arm, so it goes through this point. And if it's in standard position, as they all will be for what we're working on, it's starting from the positive x-axis. So the angle theta is going to be this theta here. We've learned about related acute angles before. It's going to be the angle between the x-axis and the terminal arm here. I can make a right triangle if I wish to, drop a straight line over here, and go over like this. Oh my goodness. Crazy iPad. Sorry. I guess that'll have to do. So I can make a right triangle out of this. Again, I know that this side length here is going to be negative 5. This side length here is going to be positive 7. And maybe I should read what the question's asking before I go any further. Sketch the principal angle theta. All right, done. Here it is here, right? I already measured it there. There's theta. What's the measure of the related acute angle? So beta, we call the related acute angle beta. I can actually calculate what beta is because according to this right triangle, this would be the opposite side. This would be the adjacent side. You know, it's x and y. So since I know x and y, I know that tan beta equals y over x, which equals 7 over negative 5. And then I can find out what angle beta is just by doing the inverse tan of each side, that negative 1. So in my calculator, I can do it all at once, or I can do it in stages. I can go tan with the negative 1, and I can do 7 divided by negative 5. And you can see, oh, sorry, I see that my answer says it's negative 54 degrees. That reminds me of a little something I forgot to mention. Beta is always a positive angle. So if I was when I was calculating this, I made one little, I don't know if I'd call it a mistake, but something that I shouldn't have done. When I'm doing beta, I should ignore the negative in front of the 5. So I should have done 7 over positive 5. We're not going to worry about negative signs when we're doing beta because we always want it to come out positive. So I do 7 over positive 5. And the reason for that is because, again, beta is an angle between 0 and 90. And so putting negatives in there, all it did in this case was make my answer be negative. Sometimes it'll do other things as well, though. Sometimes it'll give me actual different answers bigger than 90 degrees, and sometimes negative at the same time. So we don't want that. So when you're calculating beta, don't use the negative sign in there. Do it like I did after I corrected it. So beta is 54. It's right near the middle. Let's call it 54.5 degrees just to feel good about that. So beta is 54.5 degrees. That's this angle in here. That's what we weren't, I mean, it's good to know that because we can use it to help us solve problems. But what we really want is theta, right? Luckily, beta and theta are related. That's why we call beta the related acute angle. The connection between beta and theta when beta is in quadrant 2 or when theta is in quadrant 2 is they have to add up to 180 degrees, right? These two angles here form a straight line, 180 degrees. So I can easily get theta now that I know beta by doing 180 degrees minus beta, which is 180 minus 54.5, which equals, what, 125.5? I think that's right. So that's how we can find, if all we have is a point, we can find out what the angle is related to that point, the principal angle, but we need to use the related acute angle. And again, when we do the related acute angle, we drop the negative signs, if there are any, and then we have to do that extra step where, in this case, being in quadrant 2, I subtracted it from 180. Just to point out something that might come up later, what if our terminal arm ends up being in quadrant 3? Well, then theta would go all the way around to here. It would go all the way around past 180 plus beta. So if I found out what beta was in quadrant 3, instead of subtracting from 180, I'd add it to 180 because I'm going past 180. All angles in quadrant 3 are past 180. And if it was in quadrant 4, somewhere, say here, I'd be going all the way around here, almost 360 degrees, right? Going to there is 360 degrees. So if I found beta in here, I would do 360 minus beta if it was in quadrant 4. So I have to do different things with beta depending on which quadrant it's in. All right, is this the last example? Yes. Angle theta is a principal angle that lies in quadrant 2 such that theta is between 0 and 360 degrees. That's a given if it's a principal angle. And we're given that cosecant of theta equals 3 over 2. Determine the exact values of x, y, and r. All right, we got enough information to work with. We simply have to draw a sketch so that we can see what's going on. So we're told that there's an angle in quadrant 2. So if it's in quadrant 2, we know where that is. And it doesn't tell us what, though. So let's just draw randomly like this. So there's the terminal arm in quadrant 2. Cosecant, remember, is one of our reciprocal ratios. Cosecant is hypotenuse over sine. It's the reciprocal of sine. So not hypotenuse over sine. I just had sine on my brain. It's hypotenuse over opposite. Sine is opposite over hypotenuse. Cosecant is the reciprocal of that, so I flip it upside down. So from that, I can get a couple side lengths. I know that the hypotenuse has to be 3 units long. If I draw, let's make this into a triangle, say that this is 3 units, that means the opposite side has to be 2 units. So I already know that y is 2, r is 3, and x I can calculate, again using Pythagorean theorem. It's equal to the hypotenuse squared minus one of the other sides squared. And so it's the square root of 9 minus 4, so it's the square root of 5. So there's my x, y, and r values. That's right, this is root 5. Sketch the angle in standard position. Okay, well, the angle is this, called theta, so that's done. Determine the principal angle theta and the related acute angle to the nearest degree. So again, we always start with the related acute angle. I know what, and by the way, again, I guess as I look at this, I realize there's something I left out. It's not just root 5, it's negative root 5 because of the fact that it's on the negative x-axis. I know that in this triangle, we can't, there's nothing about the triangle itself that tells us it should be a negative root 5, but because of where it is on the Cartesian plane, it should be a negative root 5. So I need to stick the negative sign there as well. That's my actual x value. So again, my bad, but I did correct it, and hopefully that makes sense. If not, just review what I just said. Pause the video and review it and go back if necessary. Anyway, so we always want to find beta first. Since I know all 3 sides, I was starting to say, I have my choice to use sine, cos, or tan. I'll probably just stick with sine because, as we know in quadrant 2, sine is positive because we're using opposite and hypotenuse, both of which are positive values. So sine beta equals 2 over 3. If I did cosine or tan, I'd have to ignore the negative in front of the root 5 for the x. So I can do that. I'd rather just work with positive values. So beta is going to equal the inverse sine of 2 over 3, which on my calculator is, I'll just do 0.6 a bunch of times because that's what 2/3 is. And I get about 42 degrees. So beta is 42 degrees. So this angle in here is 42 degrees. That means that theta, the one that I am, generally the principal angle that I'm interested in quadrant 2, again, it's going to be 180 minus beta. So it's going to be 180 minus 42, which equals 138 degrees. So there's theta, there's beta, and that part's answered. Determine the least negative angle that has the same ratio. Well, as we know, we can have multiple angles going to the same terminal arm. And any angle that goes to the same terminal arm is going to have the same ratios. So the least negative one would be one starting at the positive x-axis, but going this direction. So there's negative 90, negative 180 to get to here, and I keep going until I get to here. So going to 180, going to the negative x-axis was 180, and I'm going beta degrees past that. It's going to be, what do I want to call this one? Trying to think of what value I could call that. Let's call it this. All right, so this one's going to be negative 180, because I went again from here to here is negative 180, plus negative beta, because I'm going beyond that by beta degrees until I get to that terminal arm. And they're all negative because of the direction I'm going. So negative 180 minus 42 degrees would be negative 222 degrees. Now this angle and this angle should add to 3, if I ignore the negative sign, should add to 360. And they will, because when you put them together, theta and phi, I believe that's what that one's called, just another Greek letter. I was trying to grab one, and my Greek's getting rusty, but I'm pretty sure that one's called phi. Those two angles need to add to give the full circle of 360.